Bismillahirrahmanirrahim. Welcome to Transistors and Application series. This is the episode number 9. In the previous episode, we are discussing about the collector characteristics curves, and in this episode, we will also try to discuss these concepts, but in details. So, first of all, let's start from the cutoff region. Cutoff region, as the name indicates, that in this region the transistor does not conduct, and our output current is zero, as the normal p-n junction diode. These are the forward bias region, and this is the reverse bias region, and this is the current increased here on the upper side, and current is reverse current is increased in the downward here, and this is the voltage. And we expect that in the forward bias it is allowed to increase current, but in reverse bias it is designed such that it can block all the current in the reverse bias direction. But this is the breakdown region, and it will reach after when we cross a certain limit of the voltage that is not that manufacturer does not design a certain diode to operate in this region. If we cross this threshold voltage, then definitely we will cross the limit of the threshold voltage, and our diode will burn, and this is the threshold voltage, and then current increase suddenly. Same is the case for the cutoff region. You can think that in cutoff region our both base emitter junction and base collector junction are in reverse bias. Both are in reverse bias. Base emitter junction is also in reverse bias. Base collector junction is also in reverse bias state. When base terminal is open, this happen only when base terminal or lead is open. For example, this is a simple NPN transistor, and let's say this is a limiting resistance, and this is also a limiting resistance. And if we let's say here we connect, but what happens? But when we do not connect here anything, here is a switch, and let's say this is an open switch, so there is no connection on a base terminal, and the simplified representation for this is this: emitter, base, and collector. Here emitter lead is open, while collector is connected via a limiting resistor here, look just like this. It looks like that. This hide this portion, this base portion. I will try to color this portion is hidden. This portion, there is no portion, or you can see that we can draw a new this is a collector, this is an emitter region, and this is look like this. This is an open circuit, and there is no path between emitter and collector, because there is no base VVB, base voltage, and biasing voltage at B. So both junctions are collector base junction, and base collector junction and base emitter junction are in reverse bias state, and when they are in reverse bias, no collector current, that is our output, and IC is equals to 0. But this is an ideal case. In practically cases, IC often called IC EO, that is called collector to emitter with base open. ICEO means collector to emitter, because this is collector emitter situation right now. At collector emitter current with base open. So you can understand this term. When this ICEO is nearly zero, but not actually zero. There is a very small leakage current. So this is a case like here you can see that here this is a case that little very small leakage current. Same is the case in this here there are a very small leakage current, and in this situation the voltage when we connect our voltmeter terminals here and at collector and at emitter, means to say when we collect our voltmeter here VC collector emitter voltage at collector with respect to emitter. In other words, here this is the voltage at CE collector meter is just that is VCC. VCE is equal to VCC because there is no drops, there is no terminal here. So all the voltage that is VCC is here VCE, but this is an ideal case. In practical cases this is a little bit lesser, so we can write here nearly approaches to or approximately equal to VCE. So this is the situation when it is a cut-off region. In other words, and the graph of this is looks like this, and this is a situation, a leakage current, and at this leakage current you can see that our VCC is equals to VCE. Here VCE is increasing towards right side and IC is increasing towards upper side. At this point here approximately 0.7 volt ULE, but it can be varied, depends upon bipolar junction transistor to transistor, and this is, let's say, 0.7 volt. This is often called VCE saturation point. Now what is saturation region? What is saturation region? Saturation region is simple region. For example, let's start our this bipolar junction is operating in a normal region. What is the normal or active region? Normal region is this when this base collector junction, base emitter junction here, this is a forward bias, and base collector junction, that is reverse bias. This is a normal situation. Let's say this is the situation, but this situation happens when base is VBB is less than VCC, because when because you can see that emitter, base, collector, this is P and this is N and this is N, NPN. So here this is positive and here this is also positive. This is positive is coming from VCC and this positive pulse is coming from VBB. This VBB tries to forward bias the base collector junction, because positive is connected to the P and its negative is coming to the this terminal here. But VCC tries to reverse bias the base collector junction. Usually in active region VCC is much greater than VBB. So that's why base collector junction is reverse bias due to this VCC is greater, and VCC reverse biases the base collector junction because positive pulse is connected with the N region. So that's why. So let's start from this normal region when VCC is greater than the VBB, and it. Now let's discuss that we are going to increase the VBB. But in active region VBB is much lesser, so that's why I explained the this is in reverse bias. Now I am trying to increase the VBB and let's see what happens. I try to increase and let's see what happens. If I increase VBB, of course in this region, if VBB is increased due to this increase in a voltage in a closed loop, this IB also increase because directly proportional base current increases. And when base current increases, because this is an active region And remember that there is a formula that is called beta DC is equals to collector current divided by base current. If we rearrange this formula, that this becomes IC is equals to collector current equals to beta DC multiplied by IB. If IB increases, it means collector current also increase, so IC also increase. But there is another relation, but before going to this relation, I want to explain that this relation only valid until this base collector junction is in reverse bias state. Remember, this is very important point I am explained. This relation is only valid, when base collector is reverse bias and base emitter junction is forward bias. But because this is when base collector junction is reverse bias and base emitter junction is forward bias, this is called an amplifier region, because amplifier transistor is operated as an amplifier. When transistor operate as an amplifier, definitely then we can say that there is a gain. And that then we can say that there is a gain and there is a formula for the gain. But when this is not an amplifier as region, active region, and not in amplifier state, so there is no gain and this formula will not valid in saturation region. But right now we say that we are increasing, not reached that in a situation when VBB exceeds from the VCC. When VBB exceeds from VCC, then this formula not valid. But right now we are increasing and we had not reached to this point that VBB exceeds from VCC. When VBB increases, IB increases and IC increases. When IC increases, collector current increases. There is a relation called VCE is equals to VCC minus ICRC. This relation, applying Kirchhoff voltage law to this loop comes from this side. Here IC if increases, you can see that if IC increases, definitely this decreases because this product increase product of this it will be subtracted from VCC, and answer will be of course less if IC increases. So VCE decrease means to say that I'm going to change the color. We have moving toward this side because VCE is decreasing. Toward right side VCE is increasing, but towards moving left side VCE is decreasing. And if we goes decreasing and we reach a point that is called VCE saturation point. VCE saturation point is a point when VBB increased from VCC. That is the very important point. If you focus this point, this is the total summary of today's episode and the previous episode. And when this point reaches, when VBB crosses the VCC, definitely this positive is greater and had a higher concentration than this positive, and this positive current will forward bias this PN junction because this is higher concentration. So this base collector junction becomes forward bias, and when this base collector junction becomes forward bias, while base emitter base junction or base emitter junction is already forward bias, both are in forward bias state, then this state is called saturation state. And remember that at this state this formula does not valid now when this happens, and when this happens this formula doesn't valid. Remember that if we still increase IB, when after this situation when both junction become forward bias, if we still increase IB, VBB increase, IB increase, then IC constant does not increase further. Why? Because this formula does not valid. If this formula doesn't valid, we increase IB, but This, there is no relation like this. Cross this, there is no relation, hide this. So that's why I see constant. So this is a situation, for example, let's say here we increase this IB increases, this is a for certain IB, IB1, IC increases, IC is increasing toward this side, let's say this is IC also 1, IC2, when IC2 we increase IB to IB2, IB2, remember IB1 is IB2 is greater than IB1, IB3 is greater than IB2, IB4 is greater than IB, this is IB, I base current 3, if I further increase base, that is I base current 4, if I further increase, that is I base is equals to 5. All the base current I increasing towards here. When I increase base current, you can see that collector currents are also increased, but here this point, this is called V saturation point. This point, you can see that this is saturation point, and when this saturation point reaches, further increase in the base current, further increase, if I goes to IB6, the collector current not reaches same curve for the IB6. This collector current reaches now maximum. This is called maximum point. This is called IC saturation point right now. If I further increase IB, IC does not increase, and this is called the IC is now at a saturation point, or in other words, IC saturation point is the maximum current of the IC, and we cannot increase the IC furthermore. And here these are the same curves like here, this is the reverse bias region. If it further goes increase, and these are the active region, normal region that we already discussed in the previous episode. And here at the end I want to say that this is the last, this is the minimum cutoff region and lowest curve, and which is called the cutoff region of the diode, cutoff region of the bipolar junction transistor. And this is the last point, least point, this which is called, after which it goes into the breakdown region. If we connect these 2 points, IC saturation point and the last point of the cutoff region, this is called the DC load line. Whole topic is covered right now. The last topic we have to discuss is the DC load line, but I explain in a single line, very simply, that if we connect the IC saturation here and our cutoff region, and we connect this is called the DC load line. And remember that this DC load line is the total region of the active region, and we can operate our BJT as an amplifier. And this DC load line region covers the all the region in which you can see that all the curves are in an active region. And if we when this DC load line touches these at the points, these points, when it touches, it cuts and meets these curves at the point, these points are called Q points. We will also discuss this in detail, but not in this series, later on in the coming series, another series. Okay, this is not our topic right now in details, but right now I want to say another thing. At this situation, in active region, our base collector junction is, this base collector junction is in reverse bias, and base emitter junction is forward bias. So we had discussed the 3 situations in which both reverse bias, both forward bias, one forward, one reverse bias. So that's the thing from the episode 1 I said that we will cover these things when we grow and we covered the episodes. And this is the time I can say that we covered the 3 situations right now. So in the coming episode we will also try to clear these concepts with the help of an example, and we will try to find out that how to calculate that our bipolar junction transistor is either in saturation region or in cutoff region or in an active region. So how we can calculate, and we want to if we want to calculate, these are the questions that come in exams. So discussion will be continued next time. Already I take some extra time, so take care, watch and grow. See you next time.